Hi everyone, how's it going? Welcome to the Master Networking for Hackers mini course. This mini course is a part of my Offensive Hacking Cookbook course, so if you want to become a job-ready penetration tester and want to learn real-life hacking skills, then this is the only course you need. For more information on this, please check out the link in the description. With that being said, let's start and master computer networking. Alright my fellow hackers and cybersecurity enthusiasts, welcome to the networking refresher module of our course. Now I know what you're thinking. Networking? Isn't this supposed to be a hacking course? Well, let me tell you. Having a solid understanding of networking is absolutely crucial if you want to become a successful hacker or pen tester. Think about it. How can you expect to hack into a network if you don't understand how it's structured, what protocols are being used, or how data flows through it? It's like trying to break into a house without knowing the layout or where the doors and windows are. In this module, we are going to cover the networking basics that every hacker needs to know. And trust me, we are not going to sugarcoat anything. We are diving straight into the nitty-gritty details that will give you a real edge in your hacking endeavors. Here is the list of all the topics that we will be discussing in this entire module. The topics are chosen very wisely, keeping the practicality of the concepts in mind and avoiding unnecessary fillers. First, we will start off with the IP addresses. We will learn and understand what they are, its types and classes. Next, we will look into the MAC addresses, followed by the client-server model and DNS. Post this, we will thoroughly understand the TCP and UDP protocol. Moving on, we will look into some common ports and protocols that are frequently used. After that, we will take a deep dive into the OSI model and the concept that make the web works. And at last, we will go through the infamous subnetting section to mark end of this module. On that note, let's get started with our networking journey without any delay. I'll see you in the next video where we will discuss about the IP address. So I'm really excited to take you on a journey through the world of IP address, which are like the backbone of communication on the internet and computer networks. Talking about the learning objective in this section, I can assure you that by the end of this, you will know everything about the IP address, its types and working. So let's get started with the basics. What is an IP address? An IP, Internet Protocol Address, is a unique numerical identifier assigned to every device connected to a network that uses Internet Protocol for communication. It consists of 4 numbers separated by periods that can be called dots, such as 192.168.0.1. Each number can range from 0 to 255, giving us over 4 billion possible combinations for IPv4 addresses. It uses a 32-bit addressing scheme that uses TCP/IP host addressing scheme. Example like we have here is 192.168.1.152/24. So in layman terms, you can think an IP address is like a unique identifier for devices connected to a computer network. Just like you have a mailing address nearby your house, not your actual house. I'll tell you in the next module why we are not considering IP address as our home's address. As of now, we can consider IP address as our mail address in our city for receiving letters and packages. Like that, only devices on the network need an IP address to communicate with each other over the internet or a local network. Understanding IP address. So here I have created a table that has a bunch of zeros and ones to understand how an IP address is formed. As we learned in the previous slide, each address uses a 32-bit addressing scheme. What does that mean? That means each set is made of 8 bits. Now the number we can see here has a from range of 0 to 255. The minimum it can be a 0 and the maximum it can be 255. So I have 8 bits here, 1, 2, 3, 4, 5, 6, 7 and 8. So IP address form, one octet is formed based on 8 bits. There are some numbers in the front row also, like 128, 64, 32, 16, 8, 4, 2, 1. What is the similarity between them? So the similarity between them is that they are related to the number 2. Which is binary. Binary consists of only two digits, zeros and ones. So the output can either be 0 or it could be 1. So if we add all these, Like if I add 128 where the 1 is true and 0 is false, so I'll add 128 plus 64, it gives me a 192. Then if I add 128 plus 32 plus 8, it gives me a 168. And here is only 1, so there is 1. And for this 128 and 16 and 8, so it gives me 152. So that's how an IP address is formed. So we got the number 192.168.1.152. So that's how it's been calculated. Okay, so next we have IPv4 and IPv6. IPv4 has been the backbone of internet for decades now. But with the rapid growth of connected devices, we are quickly running out of available IP addresses. Then enters IPv6, the next generation protocol, which was designed to solve this particular problem and to provide a virtually limitless supply of IP addresses. So we will look into the differences between both of them, starting off with the address size, which is 32-bit for IPv4 and 128-bit for IPv6. The next is address format, where IPv4 addresses are separated in 4 numbers using dots, whereas in IPv6, it has 8 groups of 4 hexadecimal digits separated by colons. Okay, now the number of addresses. This is an important one. In IPv4, we can only have 4.3 billion IP addresses, and in IPv6, we have virtually limitless, as we are talking about 2 to the power 128 here. Next is the address configuration. In case of IPv4, it is either manually or using a DHCP server. However, in IPv6, there is an automatic assignment. At last, the routing protocols in use. So IPv4 uses RIP and IPsec, while IPv6 uses RPing and native IPsec. Types of IP addresses. So in the previous slide, while talking about the IPv4 addresses, we found out that the IPv4 addresses, which is a common IP address in use in today also, can only have up to 4.3 billion addresses. However, last I checked, the total population on our planet Earth exceeds more than 7 billion, and as we know, every device on the network have to have an IP address in order to communicate with other devices. Talking about my home only, I have more than 5 smart devices that are connected to the internet, and I'm sure you also might be having the same. Now the question arises is that if we can only have 4 billion IP address and the total population on the planet is above 7 billion, where one person is at least using more than one devices, then how we are dealing with this? To understand this, we have to look into the types of IP addresses. So every device on the network has 2 IP addresses. Let's say your phone. So your phone will have 2 IP addresses. One is the public IP address and the other one is the private IP address. So what is a public IP address? Public IP address is an internet address that is assigned to any device that directly faces the internet. It is unique and identifies the device on the internet. It can be accessed from anywhere on the internet, making it useful for hosting websites or other services. Public IPs can be obtained from ISPs or purchased from companies that provide them. Private IPs, on the other hand, are also known as local IPs, are used within a private network and do not route over the internet's backbone infrastructure like public IPs do. So the public IP address of the device which is used to connect to the internet is different from the private IP address of the device that is used to communicate locally. But how both of them work in a sync? It is because of an awesome technology called NAT, or network address translation, which we will be discussing in the next section. Okay, to check the local IP of a system, I can go to CMD. So I'll go to search and type CMD. So I have a CMD prompt, command prompt, Windows command prompt open here, and I'll type the command ipconfig. So I have a lot of output here, but this IPv4 address. So this is my IPv4 address, my local private IP. It's 10.142.27.52. And if I want to check my public IP address, so I can go to a browser and type what is my IP, and it is showing me that this is my IP. There are other websites also that can give more information. So it is showing me my public IP address. So IPv4 has been detected. It is showing me my city, it's Stockholm, and my country is Sweden. So that's how you can find out your public IP address, and to find your private IP address, you can use the ipconfig command in Windows, and in Linux it have ifconfig, which we will discuss later. And to find out more information, you can also use a all flag with the ipconfig command. So it will give a lot more information. Okay, now coming back to the slides, we have network address translation NAT. Network address translation NAT is a technique used to conserve IP addresses and provide security by mapping one or more private IP addresses to a public IP address. Let's look into the picture we have here. There are a bunch of devices which have their own private IP addresses. When they have to communicate to the outer world via internet, they need a public IP address. There is where the NAT comes into the picture. NAT is not a hardware technology, rather it is embedded into your router only. So whenever a private IP address, let's say first computer wants to connect to google.com on the internet, NAT will take its private IP address and forward the request to the Google with the public IP address. Now the thing to keep in mind here is that there is only one public IP address for all the private IP address. So when the Google have to reply to the forwarded request, it will send the reply to our public IP address, which NAT will then transfer to the respective private IP address that have made the request. I hope you have understood the basics of NAT and its working. Let's move forward to this section where we will discuss the classes of IP addresses. Classes of IP addresses. So here we have a picture which shows some classes of IP addresses. Generally, there are 5 classes of IP addresses, but the top 3 are the most in use. The picture here is showing the classes of private IP addresses. There is a public one also, but the base skeleton of its working remains the same. So first we have a class A. The network number it start off is in the 10 range, like 10.0.0.0. The network mask, it has its 255.0.0.0. We'll look into it later thoroughly, and the number of networks it can have is 126. Now the number of hosts it can have, it is more than 16 million. So whenever you are dealing with a class A network, it is generally related to a big corporation and organization. Next we have class B. The network number in it start with 172 range, like this 172.16.0.0, and the network mask is 255.255.0.0. The number of network it can have is 16,383, and the number of hosts it can have is 65,024. So if you are dealing with such network, then it might belongs to a medium level organization. At last we have class C. This is one of the most common types. We have already seen it while checking our private IP addresses. Let's start off with 192.168.0.0 and have the subnet mask of 255.255.255.0, and it can hold up to 2,097,151 number of networks. However, the number of hosts it can have is 254, which is ideal for small organization and a home network. The thing to notice here is that all the 3 classes is the number of network and number of host. As the number of network decreases, the number of host increases, and as the number of network increases, the number of host decreases. The reason behind this will be cleared more in the subnetting section, so stay tuned. As of now, we are moving into the next section where we will learn about MAC addresses. So let's start with the basics. What is a MAC address? A MAC address is a 48-bit physical address which uniquely identifies each device on a given network. It is assigned to the NIC or network interface card of each device that can be connected to the internet. So it is basically like your home physical address. That's what I was referring while we were learning about the IP addresses. So IP address gives information, the city and street you are living in. On the other hand, MAC address gives information about your specific house number or address. These are expressed in hexadecimal notation, for example 0123456789AB, in a 48-bit address, and often considered permanent, but in some cases can be changed via software or tools. Okay, so to check the MAC address, we'll go to CMD and we'll type ipconfig dash slash all command. So this will give a lot of information. We have already looked into it. So let's find out the MAC address. So the MAC address will be, okay, so here is my MAC address. This is the physical address and my MAC address is 346059FF 5B3D. So this is my physical MAC address or the NIC address that is hard coded and just belong to my machine. Okay, so MAC address format. Talking about the structure of the MAC address, the first 3 octets or 24 bits represent the organizationally unique identifier OUI, which identifies the manufacturer of the NIC. So we can check the manufacturer of the MAC address with a MAC lookup website. Where I can say MAC lookup, and it can give me a lot of. There is a website named maclookup.app. It is, yeah, this one. So here I can put a MAC address. Let's put it from here. So entering the MAC address reveals the manufacturer name and its address. So it is showing me TP-Link Corporation Limited. So it is showing me the my NIC manufacturer is TP-Link and its particular address. Okay, now coming back to the slides. So we have talked about the first 3 octets. The remaining 3 octets or 24 bits are the network interface controller NIC specific portion, ensuring each NIC has a unique MAC address. So that's all for the MAC address section. I will conclude this and we'll see you in the next one. Client server model. There are 2 types of fundamental architecture models that we use in modern computer networking. One is the peer-to-peer model and the other one is the client server model. Let's understand both of them in detail. First, we have peer-to-peer. In peer-to-peer model, both remote processors are executing at same level and they exchange data using some shared resources. In simple terms, a P2P network has no central server or authority controlling the network. Instead, each peer directly communicate and share resources with other peers. Then we have client server model. In this, one remote process acts as a client and requests some resource from another application process acting as a server. In layman terms, the requester for the data will be the client and the provider who is fulfilling the request is the server. To understand this properly, let's take an example of the market. Suppose you want to buy a flashy new Nike sneaker, let's say Jordan 2077, and there are 2 ways to get those pairs. One is to go to a showroom or shop that deals with the concerned sneakers and get it from there. The other route is that you connect a seller just like you. The seller might be a sneakerhead himself and demands for another sneaker in place of the one you want. It's kind of a barter system. So keeping the above analogy in mind, we can conclude that if you buy the sneaker from the shop owner, it will comes under the client server model, where the client is you and the server is the shop owner. On the other hand, if you buy the sneaker from other seller like you in exchange of one of your own, then it will come under the P2P model, where both parties exchange information equally and share resources. Let's understand the information flow in both of them using the below picture. As we can see in the client server model, different types of devices like PC, laptop and smartphones all are requesting data from a centralized server, and the server is responding to all their requests. On the other hand, in P2P network, all the devices can communicate to all other devices to the network. Whoever is capable of fulfilling the request in this case will make a connection with the requester and provide the data accordingly. So that's all for the client server model, and I will see you in the next one. Okay, now we will learn about DNS or domain name system. which is one of the most important protocols supporting the internet. What is DNS? DNS translates and maps alphabetic domain names like websites, web addresses, or names to the numeric IP address of computers or server, and it is also capable of performing the reverse process. It uses User Datagram Protocol or UDP, and its service uses port number 53 to operate. Some domain name examples like .com, .gov, .edu, .org are some of the top level domains that are also called TLD names. Example of a domain name is www.google.com, which has its IP address 142.250.187.238. Machines over the internet uses IP address to communicate with one another. However, we as humans cannot remember all the IP address of our favorite websites. That's where DNS comes into the picture. It uses common human readable name like google.com and maps it to its complicated, hard to remember IP addresses like 142.250.187.238. In short, the main feature of the DNS is to map the google.com name to its corresponding IP address. It is like NAT we discussed earlier. Like NAT translate private IP addresses to public IP addresses and vice versa. DNS does the same with the domain name like google.com to its IP address and vice versa. Now to check the IP address of google.com, we can open up a command prompt, and there is a command called host in Linux and nslookup for the Windows. So nslookup google.com, so nslookup google.com will give us the IP address of google.com to us. Next, if we want to check the name server that we are using, the DNS name server we are using, we can use the ipconfig command and it will show us the DNS server. So this is the DNS server IPv6 address that I'm using, and this is my gateway's IP address. There is also one command netsh interface IPv4 show DNS servers, and it will show all the information regarding the DNS server. So this is the IPv4 address of my DNS server. Here was the IPv6 one, and this is the IPv4 address of my DNS server. So that's how you check a DNS server in a Windows machine. And once again, if you want to find the IP address of a particular domain name in Linux, we use the host command, and to find the DNS server we use a command systemd that resolve status, then we'll grep for DNS servers. So this is for finding DNS name server in Linux. Now coming back to the slides, there are three types of name servers. These are root servers, primary servers, and secondary servers. Number one, we have root server. Root server is the top level server which consists of the entire DNS tree. It does not contain the information about domains but delegates the authority to the other server. Think of this as the internet's supreme directory assistant. When you want to find a website, let's say www.inventyourshit.com, your computer first asks one of the 13 root name servers. Where can I find the information about .com domains? The root server then points you towards the .com name servers. Then we have primary servers. Primary server stores a file about its zone. It has authority to create, maintain, and update the zone file. These are the name servers that actually hold the address records for a particular domain, like a local directory listing. Your computer then asks the authoritative name server designated for inventyourshit.com what is the IP address of inventyourshit.com. The authoritative name server responds with the IP address you need to access the website. At last, we have secondary servers. Secondary server transfers complete information about a zone from another server, which may be a primary or secondary server. The secondary server does not have authority to create or update a zone file. Let's understand how DNS works step by step. We will consider the picture below for this. But before passing any request on the wild internet, the requested website is first checked in the local DNS cache stored on the machine. If any entry of the target website is not found, the DNS request flow move to the next step. So the first step we have is when we type www.example.com into our browser, it asks the local DNS server for its IP address. Here the local DNS server is at the ISP's end. When the local DNS server does not find the IP address of the requested domain, it forwards the request to the root server and again inquires about the IP address of it. The root server replies with the delegation that I do not know the IP address of example.com but know the IP address of DNS server. The local DNS server then asks the .com DNS server the same question. The .com DNS server replies the same, that it does not know the IP address of example.com but knows the DNS IP address of example.com. Then the local DNS server asks the example.com DNS server the same question. Then example.com DNS server replies with the IP address of example.com, and now the local DNS sends the IP address of example.com to the computer that sends the request. I hope you understand this. So this particular image shows a general flow of how DNS works. On that note, I will conclude this section and we'll see you in the next one. Alright my fellow hackers, it's time to dive into the heart of network communication, the TCP and UDP protocols. These two workhorses are the foundation upon which countless applications and services are built, and as hackers, understanding their intricacies is crucial for identifying potential vulnerabilities and executing successful attacks. I have listed the difference between both of them in this nice looking table, so let's go through each of the pointers one by one. Let's start with the connection type. So the TCP requires an established connection between a client and a server before transmitting any data. If there is no connection, no data will be followed. It is as simple as that. Talking about UDP on this, it is a connectionless protocol. Unlike TCP, no connection is needed to start or end a data transfer. Next is the data sequence. In TCP, data is sent in a sequential or specific order, whereas in UDP, this is not the case. After this, we have data retransmission. If in case a data packet is lost while transferring in TCP, it will retransmit it, while on the other hand, UDP doesn't care about all this extra work. Next is delivery. As we discussed earlier, TCP is a connection-oriented protocol and also retransmits whenever required. So the delivery of the data is guaranteed, whereas UDP does not guarantee anything. You are at your own risk. Moving on, we have checking for errors. TCP gives us this, but for UDP it depends on the mood. And at last we have speed. Now in this particular comparison, we have been shitting on UDP, but in this point UDP is a clear winner. As we know, TCP needs connection. It sometimes retransmits and guarantee delivery, but due to all these features, it comes slow sometimes. While on the other hand, UDP is all about speed. You can think TCP as a lovely supporting wife that mutually accepts your love and gives back with more. But on the other hand, UDP is like that one-sided crush who likes speedy dating, and all you can do is to shower connectionless data packets to it with maximum speed with no guaranteed result. Keeping the jokes aside, we can use TCP where we will need guaranteed delivery of data and speed is not the priority, like while transferring funds from one bank to another. While on the other hand, UDP is used in scenarios where speed of the data is priority, like video streaming and conferencing, where delay can cause an inconsistent and unpleasant experience. TCP three-way handshake. To understand the working of TCP protocol, we have to understand the TCP three-way handshake. Imagine you want to have a conversation with someone over the phone, but you need to establish a proper connection first. The three-way handshake is like the initial back and forth you go to set up the call. The first step is you calling the other person's number. This is like sending a SYN or synchronized message saying, "Hey, I would like to start a conversation with you." If the other person is available, they will pick up your phone and respond with a SYNAC or synchronized acknowledge. This is them saying, "Sure, I'm ready to talk. I heard your request to start a conversation." When you hear them pick up, you confirm by saying "ACK" or "acknowledge." This final acknowledgement establishes the connection, and you can now start your conversation over the open line. The three-way handshake ensures that both parties are ready to communicate and have acknowledged each other's initial sequence numbers before data transfer begins. It's like making sure you and the person you're calling have properly greeted each other before launching into the conversation. This process prevents scenarios where one side thinks a connection is open while the other side thinks no connection has been made. The three steps makes the connection setup more robust and reliable. The handshake also allows both parties to negotiate parameters like the maximum data size they can send or receive in each chunk. It's like agreeing on how much you can say in one go during your conversation before pausing for the other person to respond. So in simple terms, the three-way handshake is an initial exchange of messages that establishes a reliable data connection similar to setting up a phone call properly before starting to speak. Next, we are working of UDP. So imagine you are sending letters through the postal service, but you don't really care if some letters get lost or arrive out of order. UDP is like that unreliable postal service. With UDP, you just keep writing letters, data packets, and putting them in an outgoing mail without waiting for acknowledgement that the previous letter arrived safely. You simply send the datagrams out rapidly one after another. You just keep writing letters and putting them in outgoing mail as fast as possible. It's a best effort approach. So letters may arrive quickly, some may arrive late, some may get lost, and some may arrive out of order, but you don't care, as long as most of the important information gets through without too much delay. This works well for applications that can tolerate some data loss like video streaming, online gaming, DNS lookups, etc. It's much faster than a formal connection-oriented protocol like TCP that establishes a reliable communication channel first before transferring data. The trade-off is that UDP is unreliable and unordered, but it's lightweight and super fast for time-sensitive data transfers, where occasional data loss is acceptable. It's like a super speedy but unreliable postal worker who just keeps moving your letters along as quickly as possible. I hope you have understand the concepts related to TCP and UDP and the TCP three-way handshake. That's an important one for us. So on that note, I will conclude this section and we'll see you in the next one. Now we will look into some common ports and protocols that are used all over the internet. Most of them we will encounter frequently as we progress further in this course. So you should be at least familiar with the common and well-known ones. Let's start with the basics first. What are ports? A port in computer networking is a logical access channel for communication between two devices. The total number of ports are 65,535. The top 1023 are well-known ports. From 1024 to 49,151 are registered ports, and from 49,152 to 65,535 are dynamic or private ports. Let's understand this with an analogy. Imagine your computer is a big office building with many different departments and services. Each department has its own entrance door, which can be called port that people use to access the specific service. For example, the main entrance or port 80 leads to a website department that handles HTTP web traffic. The secure entrance on port 443 goes to the e-commerce section that handles HTTPS secure web transactions. The mailroom door or port 25 is where SMTP is received and sent out. Next, the file transfer lobby or ports 20 and 21 allows people to upload and download files using FTP. Just like these different entrances allow people to access the various services offered in the office building, service ports on a computer allow network data to access the corresponding software applications and services running on that machine. Now we will understand what a protocol is. Protocol is defined as a standard way for computers to exchange information. Imagine protocols as the rules and customs that allow people from different countries and cultures to communicate and interact with each other effectively. Just like we need a common language or a set of gestures to convey meaning, computers need agreed upon protocols to transmit data successfully. Network protocols are kind of like the languages that computers speak to exchange information over a network. They define the vocabulary, grammar, and etiquette that computers follow to talk to each other in an understandable way. Some common protocols used in computer networks and the internet are TCP, UDP, and IP or Internet Protocol. Here are the list of some common ports and protocols. First we have is port 20 and 21 for FTP. Port 20 is used for transferring files in active mode FTP sessions, while port 21 is used to send FTP commands between the client and server. Next we have port 22 for SSH and port 23 for Telnet. Both of the ports are used to access remote machines. However, SSH stands for secure shell, thus encrypting the communication, while Telnet transmits all data like passwords in clear text, which makes it insecure. After that we have SMTP at port 25 and POP at port 110. Both of these are email related ports and protocols, where SMTP is used to send emails from client to server. POP or POP is used for retrieving emails from a server to a client. Next we have port 80 and 443. Port 80 is a default port for HTTP, enabling encrypted data transmissions. Port 443 is the default port for HTTPS, providing unencrypted communication over TLS or SSL. While port 80 is a widely used, port 443 is preferred for sensitive data like e-commerce transactions due to its enhanced security features. At last, on the TCP end, we have port 139 and 445 that belongs to SMB. Both of them are used for file sharing and printer access. Now coming to the UDP related ports, first we have port 53, which is DNS. We have already discussed about it in detail in the previous section, so I'm not going at it again. Next we have port 67 and 68. Both are used by the Dynamic Host Configuration Protocol or DHCP for communication between clients and servers. Port 67 is used by the DHCP server to listen for the client request, while port 68 is used by the client to receive responses from the server. Moving on, we have port 69, which is used by Trivial File Transfer Protocol or TFTP for simple file transfers, often for booting network devices from a local server. TFTP has limited functionality compared to FTP, but its simplicity makes it suitable for tasks like firmware upgrades on network appliances. Now we have port 123, which is used by the Network Time Protocol (NTP) for time synchronization between computers and devices on the internet. NTP ensures accurate timekeeping by synchronizing clocks to a common time source. At last we have port 168, which is used by Simple Network Management Protocol or SNMP for network management and monitoring. It allows devices to communicate with network management systems, enabling the exchange of management information between network devices and management stations. So that were some common ports and protocols that are frequently used in our ethical hacking journey. I hope you have understood it, and on that note I will conclude this section and will see you in the next one. Now we have come to one of the most important topic of this module, the OSI model. All the topics we have covered till now individually will make sense after we complete this section. So let's get started with a question. What is OSI model? So the OSI or Open System Interconnection Model is a way to understand how computers communicate with each other over a network. It's like a blueprint that helps us visualize how data is sent and received between devices. Let's understand with an analogy again. Imagine you want to send a letter to a friend. You write the letter in the application layer, put it in an envelope in the presentation layer, and address it in session layer. Then you give it to a mail carrier, which is the transport layer, who takes into a sorting office in the network layer. The sorting office figures out how to get the letter to your friend's neighborhood, to the data link layer, and finally it's delivered to their mailbox at physical layer. The OSI model breaks down this process into 7 layers, each with a specific job. Number 1, we have a physical layer. This is the physical connection between devices like cables or Wi-Fi. Layer 2 or data link layer. This layer ensures data is delivered between devices on the same network. This is done with the help of MAC addresses. Layer 3 or network layer. This layer routes data between different networks. It takes help of IP addresses. Layer 4 or transport layer. This layer manages data flow and error control between devices. This is done with the help of protocols like TCP and UDP. Layer 5 or session layer. This layer establishes and manages connection between applications. Layer 6 or presentation layer. This layer formats data for the application layer. Examples can be picture, videos and document files. Layer 7 or application layer. This layer is where applications like email and web browsers interact with the users. Each layer communicates with the layers above and below it, ensuring the data is transmitted correctly. The OSI model helps us understand how these layers work together to enable communication between devices on a network. TCP/IP model. Though we have already discussed the OSI model, we should also take a look at the TCP/IP model. The OSI model is more like a blueprint than the actual working model. The actual working model that works in the real world is the TCP/IP model, which is the reduced version of the original OSI model. Unlike OSI model, the TCP/IP model have only 4 layers. Number 1 is application layer. This is where the actual data like a web page or email is created. It's like you writing a letter to your friend. Number 2 is transport layer. This layer ensures that data is delivered completely and in the right order, like a mail carrier delivering your letter to your friend's house. Number 3 is internet layer. This layer is responsible for addressing and routing the data, like the postal service figuring out where to send your letter based on the address. And at last we have network access layer. This layer handles the physical connection between devices like the cables or Wi-Fi that allow your computer to connect to the network. So that was the OSI and TCP/IP model. This is really important while we are studying networking, and I hope you have understand it. On that note, I will conclude this section and I will see you in the next one. Okay, so in this section we will learn about the inner workings of the web, how data is transmitted, some of the topics we have already discussed earlier, which will make the things more clearer to us. Let's start with this picture showcasing a simple anatomy of the working of a web. At first, someone tried to access a website or application from their devices. The request is then forwarded to the gateway of the router to which we have connected wirelessly. The router forwards the request to other routers through cables owned by the internet service provider like Airtel, Jio or Vodafone. The other routers forward the request to other routers until they found the target server. Once the request is reached to the server, it responds back with the requested data. Information is then traveled back to our router via the same ISP cable. When it is reached to our router, it is then forwarded to the specific MAC address of the device who initiated the request in step 1, thus completing the whole journey. Anatomy of a URL. In the previous slide, we looked into basic overview of the working of web. The first step includes sending a request to the server. This is usually done by a web browser where we types a URL address like google.com and the request is thus generated. So let us understand how a URL works by understanding its parts. Here we have a photo that shows different parts of a URL. At first we have scheme. This is the first part of the URL and tells our browser how to access the website. The most common schemes are HTTP or HTTPS. The S in HTTPS stands for secure and means the connection is encrypted. The second we have is subdomain. This comes after the scheme and is optional. It is like a specific room or section within a website. For example, blog or support before the main website name. The third is the domain name. This is the main name of the website like example.com. It tells our browser where to find the website on the internet. The fourth one is the top level domain. This shows the type of TLD we are using like .com, .gov, .org, .co.uk, etc. This also tells about the type of website we are dealing with. The next is the port number. We can see here we are using HTTPS, so the port number will be 443. We already knew that from the common ports and protocol section, if you remember. Moving on, we have the path. This comes after the domain name and tells our browser where to find a specific page or file on a website. It's like giving direction to a room inside a house. The next is the query string, separator and parameter. This starts with a question mark and contains information to help the website know what specific content to show us. It's like telling the website what we are looking for. And at last we have fragment. This starts with a hash symbol and takes us to a specific section of the page, like a bookmark. It's like pointing out a specific spot on a page we want to go to. HTTP methods. Now that we have generated the request by requesting hard on that enter button after entering the URL, we will now understand how a HTTP request get transferred to the server using HTTP methods. HTTP methods, also known as HTTP verbs, are the action that a client like a web browser can perform on a resource like a web page that is hosted on a server. There are mainly 4 types of HTTP methods. These are: number 1 is the GET request. This is used for getting information from a web server. It's like asking the server to give you a specific piece of information like a web page or a list of products. On number 2 we have POST request. This is used for submitting data to the web server and potentially creating new records. It's like filling out a form on a website and submitting it to the server to create a new account and submit a message. The third one we have is PUT request. This is used for submitting data to a web server to update information. It's like replacing an old version of something with a new one, like updating your profile information on a website. At last we have delete request. This is used for deleting information or records from a web server. It's like deleting something you no longer need, like removing a post you made on a social media platform. Okay, let's see how a sample request flows to the server. So we have opened our Firefox browser. We'll press F12 on our keyboard and this will give us a nice looking developer tool option. I'll make it a little bigger. We will now go to the network tab, and if I type google.com here, let's see what happens. So there is a bunch of traffic we can see over here. Let's open up one of the requests. Let's open this request. So if we see the request, we can see the header section, and this there is a cookie section, response, timing, security. All of this we can view from here. Let's see the header section first. So this is the request that we are creating to get data from Google. So we are creating a GET request over here, and there is also a POST request. So this is a POST request. We are posting something over here. So there are multiple parameters. We will go through them one by one. But as of now, I just want to let you know how we can search for the request and how requests are made to the server. So here we can say the GET request. We can see the POST request, GET, POST, different parameters just for a single page. So there are images on this particular website. Okay, so there are images on this particular website. It is asking for cookies, so there are some cookies value also, and I have this image, and whatever is in this page, it will show in this network tab that we have made the request to the Google server just to fetch google.com search page. I hope you understand that. Okay, now coming back to the slides, we have HTTP status codes. So HTTP status codes are like a secret language that web server use to communicate with web browser. When you visit a website, your browser sends a request to the website server, and the server responds with a special 3-digit number called an HTTP status code. These codes are divided into 5 main categories. Number 1 is 1xx informational. Number 1 is the informational codes, or you can say 100 in 100 range codes. The server is thinking about our request and needs more time to process it. Then we have 200 level codes. These are also called success codes. The server has successfully received our request and is sending us the information we have asked for. And on number third, we have 300 scores, range codes, also called redirection codes. The server is sending us to a different website or a page to get what we need. At number 4, we have 400 level codes or client error codes. The server can't understand our request or don't have permission to access the page. And at last, we have 500 level codes or server error codes. In this means that there's a problem on the server side that's preventing it from fulfilling a request. So some of the most important status codes to know are like 200 OK. So this means everything is working fine as it should. Then we have 301 moved permanently. The page we are looking for, this means the page we are looking for has moved to a new address. Then we have a 404 not found. This is a famous one. That means the page we have requested doesn't exist on the server. And the 500 internal server error. So this means there is a problem with the server that's preventing it from fulfilling our request. Let's see some of the status codes through our own eyes. Okay, so I'm I've come to my web browser and I've opened up the network tab. So here last time we looked at one of the get request and one of the post request. Now we will look into the status code. So this is the status code. So 200, that means everything is fine and we have successfully retrieved the information that we asked from the server. So status code can help us determine what is the status of the request. So I can, let's see if we find another status code. We got a 204 also, and if I got a 301, I can get a 301 because so all I get from here is, let's say I ask for a particular page that doesn't exist. So I entered a particular URL, a random string, and let's see what status code we got. We got a 404 not found. Okay, so this is how the status code works. When while talking about status code, it is really important when we try to pen test or when we try to hack into the website, because we will be interacting with the website on a particular basis, and status code is a really good way to know the status of the website or a page. So that's how a lot of tools also work. So the tools we will look into the reconnaissance section, you will get to know why status codes are important. Okay, now HTTP headers. HTTP headers are like extra information that gets passed between a web browser and a web server when they communicate with each other. They are sent along with the main content like a web page or an image to provide additional details about the request or response. Some of the common HTTP headers are set cookie. In this, information is stored which gets sent back to the web server on each request. Then we have cache control. It shows the duration to store the content of the response in the browser's cache before it requests it again. Then we have content type. This tells the client what type of data is being returned, i.e. like HTML, CSS, JavaScript, images, PDF or videos. Using the content type header, the browser then knows how to process the data. And at last we have content encoding. It shows the method used to compress the data to make it smaller when sending it over the internet. Okay, now let's see let's see the HTTP headers now. So last time we looked at the status code, now we'll look at the HTTP header. So if I open any request, let's open this request, and we can see a lot of headers here. So we have a content length header, and we have a content type. So it is a text HTML what we are looking for, what we are fetching from the server. Then we have some xframe related option, and let's see if we have a set cookie. We don't have a set cookie here. Let's see another one. Let's see a get request. Do we have a cookie? No. We do have a cookie here, so it might have a set cookie option. So this is the cookie header, set cookie header. And accept encoding. So this is the encoding that the page can accept, that the request is made and the type of content it is accepting from the server. So this type of encoding is possible. We can change it also. We will look into it later. So that's all for the HTTP header. Okay, now we have cookies. To understand cookies, you have to understand how HTTP works. So HTTP is a stateless protocol. That means HTTP have no feature inherently built into it that can remember and handle requests and sessions. Think of it as like this. Like, let's say you went to a shop and the shop owner name is HTTP Kumar. Now this HTTP Kumar has dementia. Dementia is a disease where the affected person suffers from a memory loss. So you went into the shop, took whatever you wanted to buy and moved out. Now when you reach your car, you remember that you have left the car keys in the shop itself. You went back to the shop owner, HTTP Kumar, and told him about your keys. Now the shop owner have your keys with him. However, as he is a dementia patient, so he forgot who you are and denied your request for your own keys. This happens just with some couple of minutes. The same things happens with HTTP. You go to the website and you log in, let's say Instagram. Now when you try to comment on your crush's new Insta reel, a new HTTP post request is generated for this. However, as the HTTP is stateless, it will take it as a new request and will ask you to log in again. So for every request you have to authenticate yourself. Sounds like a pain in the ass, isn't it? Here comes the sweet cookies into the picture. Cookies are small text files that websites store on your computer or device when you visit them. They help website remember information about you and your preferences, like your login details, shopping cart contents, or the page you have visited. There are different types of cookies. Number one is session cookies. They are temporary and deleted when you close your browser. Second is persistent cookies. They stay on your device until they expire or you delete them. The third one is the first party cookies. They are set by the website you are visiting. And the last is the third party cookies. These comes from other websites like advertisers and track your behavior across multiple sites. So let's see where the cookies are stored. So I've opened up the developer tools option, and if I go to storage, here are all the cookies that this particular page has. So if I've logged into Instagram, my Instagram cookie will be here. So different types of cookies are stored on different types of username and password cookies, and different types of preferences cookies, as I've already told you. Session cookies, persistent cookies, some are first party cookies here, and some are the third party cookies. So every cookies will be stored here. If you want to check your cookies, you can go to the storage tab in developer option. I hope you get it. Okay, so that was the last topic of this section. I will conclude this section here only, and we'll see you in the next one. Now we have come to the beast of this entire module, subnetting. But don't worry, I will teach you how to tame it very easily. So let's get started. What is subnetting? A subnetwork or subnet is a logical subdivision of an IP network. Now the question arises is that, why do we need to do subnetting? Well, the answer is that the subnets make networks more efficient. Through subnetting, network traffic can travel a shorter distance without passing through unnecessary routers to reach its destination. Let's understand this with an example. Suppose we have a network here with some computers on it. If a computer A wants to communicate with computer F, it needs to have its address with him. To get its address, it will start a broadcast which will then be forwarded to every host. So it will broadcast here, it will broadcast to this computer, this one, and this one, and this one. Now every host will broadcast back with kind of yes or no answer. So it will give out a broadcast message for everyone. This creates a loop in the network and will create a congestion, resulting in a massive data loss and delay. So that's how we subnet a network. So what we will do, we will make a subnet of these three hosts, and then we'll make a subnet of these three hosts. That's how we can manage the packets in a particular network without having any congestion or data loss. Now that we have understand about the concept of subnetting, let's see what a subnet mask is. A subnet mask is a 32-bit address that segregates an IP address into network bits that identify the network and host bits that identify the host devices operating on that network. In simple terms, a subnet mask is a number that helps divide a network into smaller parts called subnets. It works by separating the IP address into two sections, the network portion and the host portion. Classes of IP addresses. We have already discussed briefly about the classes of IP addresses before. At that time, I have included the chart for the private IP address range. This time, I have included the public IP address range chart, so don't get confused. Now coming to the chart here, all the things are usual as before. The main thing we have to talk about here is the subnet mask. Check out the values of the subnet mask changing from class A to class C. The class A subnet mask has 1 octet in it while class C has 3 octets. Let us understand this in Excel sheet properly. Okay, so now I'm in an Excel sheet and let's take a IP address here. So I'll take 192.168.29.82. So suppose this is our IP address. Let's zoom it a bit. So this is our IP address, okay? Now for every IP address, it has 4 octets. So this IPv4 address is made up of 32 bits. And each octet will comprise of 8 bits. So 8, 8, 8 and 8 equal to 32. Okay. And each of these bits contains 0 to 255. It can contain a number of from 0 to 255. So I will make the table again. 128, 64, 32, then 16, then 8, then 4, then 2, then 1. So if we add all of these numbers, it comes to 255 total. Okay. And the bits are in binary, so it is either can be 0, it can either be 0 or 1. Okay. So if we have 1 on all of these, if we have 1 on all of these, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, so it will give the number 255. This is for the first octet. So we are talking about 192 here. So if we want 192, we can make it 0. I've already told you in the IP address section how we calculated. We made the table. So this will give me 192 if I add 128 and 64. Okay. Every octet we have these numbers. So I have this one for 192. I can have for 168, same I can have for 29, and same I can have for 82. So I have for each octet, I have these numbers, and based on these numbers, we calculate this particular thing. Okay, so for now, understand that IP address made up of 32 bits, each octet contains 8 bits, and these 8 bits can have a range of 0 to 255. So we are keeping this on hold, and let's first understand the network and host portion of IP addresses, then we will be able to better understand the subnet mask. Network and host address. The network address is used to identify the network and is common to all the devices attached to the network. It is denoted by 1. For example, 192.168.129.82/24. Here the network portion will be 192.168.129. The host or node address is used to identify a particular device attached to the network. It is denoted by 0. For example, 192.168.129.82/24. Here the host portion will be 82. CIDR. Classless inter-domain routing is a method of IP address allocation and IP routing that allows for more efficient use of IP addresses. CIDR addresses are represented using a slash notation, which specifies the number of bits in the network prefix. For example, an IP address of 192.168.1.0 with a prefix length of 24 would be represented as 192.168.1.0/24. The notation indicates that the first 24 bits of the IP address are the network prefix and the remaining 8 bits are the host identifier. But how to calculate CIDR? For that, we will have to move back to the Excel sheet. Okay, so here I've made a table based on the classes of IP addresses. So class A, class B and class C. We already know that if we add all these numbers, we will get a sum of 255. In the previous slide, we have seen that in class A, the subnet mask is 255.0.0.0 because class A only has 8 bits in its first octet. So 8 bit in first octet gives us 255 and the rest all are 0. So this also gives us /8 CIDR notation. The class B has 8 bits in first octet. So we have 255 here. Then 8 bits again in the second octet. We have 255 here. So 8 bits plus 8 bits, total will be 16 bits. So the CIDR range we have is 16 bits. Now comes the class C, the famous one. First octet has 8 bits, so we have 255 here. Second octet has 8 bits, we have 255 here. And the third one also have 8 bits, so we have 255 here. So 8 plus 8 plus 8 gives us 24. So we have a /24 notation. I hope you have understood it. Network and broadcast address. Now for the host ranges, we have some preoccupied addresses. These are the network address and the broadcast address. The network address is the first address of the IP subnet, while the broadcast address is the last address of the IP subnet. All addresses between the network addresses and the broadcast addresses are host addresses. A network address provides identity to the IP subnet. So we have looked into every major aspect of the subnetting section. Let's calculate the below parameters associated with an IP address. Here we have an IP address that is 205.150.65.0/26 and we have to calculate its class name, network ID, broadcast ID, CIDR, subnet mask, number of subnet and number of hosts. So the first parameter is the class name. We can easily find this out by looking to the table we have made here. As we can see, it is a /26 address. As per the table, it will come under the class C address type. On that basis, we have our class name, that is class C. So we can write class name is class C. Next is the CIDR. We can easily get in the slash notation. So the CIDR here will be obviously /26. We already know that. So the CIDR we have /26. After that, we will calculate the subnet mask. So we will now calculate the subnet mask. Okay. Now this is interesting. We know that the CIDR notation of this particular address is /26, which falls under the class C type address. So usually we have the configuration in type C address with 24 bits. So 8 bits here plus 8 bits 16 plus 8 bits is equal to 24. So naturally the class C has its octet like this. So we have class C, so 1111 8 bits and then again 8 bits and then again 8 bits and the last one has the last octet has all zeros. So this gives us a subnet mask of 255.255.255.0. This is generally the subnet mask of class C address, as we know that. Now that we have /26 bits, so we don't have 24. It is based on the 24 address. So 888 gives us 24 bits. So /24. But we want to find out of /26. How can we find out that? So what we will do, we will take 2 from the host portion. So we need +2. We already have 24 here and we need +2. And this is the last octet. We know that it is for the host portion for in class C. So we will take 2 from the host portion. So I can write this like this. So I have taken 2 from the host portion. Now calculating the subnet mask for this. So we have 255.255.255. We already know that for the first 3 octet, but for the last one we only have 2 bits. So we only have 2 bits, others are zeros. Now we'll get back to a table, and now adding these bits up. So we have 2 extra bits. So one here and one here. 8, 16, 24, 25 and 26. Now if we add these two, as we know how to calculate the IP address or the subnet mask, the octets. So if we add these two, we'll get the number 192. You can use calculator also. So 128 plus it's 64. So 192. So the subnet mask we will get finally here is 192. So the subnet mask we can call here is 192. So the subnet mask for this particular IP address will be this. So 255.255.255.192. I will summarize it once again. What the steps we have taken. First of all, we looked at the CIDR range. It was around the class C address. Class C address is /24. It was /26. So it comes around the class C address. So we took that class C address. Then we took 2 bits from the host portion because we have to expand it. We already have 28 bits here, 24 bits here, and then we expand it to 26 bits. Okay, then we put into our table, and then we added the upper 2 number where the bits was added, and we got 192, and that's how we got the last octets of 192. So I hope you have really understood it. If not, please rewatch the video or do it by yourself. You will get it in no time. Okay, so the next thing we have the network ID and the broadcast ID. We'll start off with the network ID. Now there is a simple formula to calculate the network ID of an IP address. That is, network ID is equal to network portion and subnet mask. So the formula for network ID is network ID is equal to network portion, and it is an AND operation. If you know digital electronics or you know Boolean algebra, so you know what AND operation is, and subnet mask. That means we have to perform an AND operation between the network portion of IP address, which is 205.150.65, and the subnet mask, which is 255.255.255.192. Now those who are not aware of the AND operation, it's really simple. Basically an AND operation is a logical operation which takes 2 input and give result as true only if all conditions or statements are true. We can easily perform AND operations online without going the manual route. Let's see how. Okay, so now we are at a bitwise calculator. So we have to perform an AND operation between the network ID and the subnet mask. So we'll get the first octet, value of the first octet from the network ID and value of the first octet from the subnet mask. So it is 255. We perform the AND operation and it gives me the result 205 in binary. Okay, so 205, I will store it here. Then 150, the second octet is 150 and 150, and the subnet mask is 255. We already know that. Now we perform the AND operation and we got 150 result. So next I can 150. Okay. The third octet is 65. 65, and we again perform the AND operation and we got 65. The last octet is 0 and the subnet mask last octet is 192. So the last octet is 0 and subnet mask is 192. We perform AND operation and we got 0. So we got the network ID that is 205.150.65.0. Okay, so I'll summarize it once again. To find the network ID of an IP address, we have to perform AND operation between the network portion and the subnet mask. I hope you understand that. So before getting into the broadcast ID, we have to calculate two things first. One is the number of subnet that our concerned IP address range can have and how many hosts are possible with them. So number of subnets and number of hosts. Number of hosts. Let's get right into it. First we will start off with the number of subnet. For this we have a formula too. Number of subnet is equal to 2 to the power n. Here we are taking the extra bit as n. As we have 26 bit, so we have 26, so we have 2 extra bit from class C address range. Typically it has /24 network range, that means 24 bits, but we stole 2 bits from its host portion. So the power of n to calculate subnet will be 2. In this case, the 2 to the power will give us 4. So 2 to the power 2 is will give us 4. That means we can have 4 subnet with this IP address range. So the value of number of subnets will be 4. Next is the number of hosts. To calculate this, we will use the formula number of hosts is equal to 2 to the power n minus 2. Now here the n is equal to the remaining bits in the last octet. So the last octet had 8 bits. Out of 8, we have already stole 2 for our subnet. So the remaining will be 6. So 1, 2, 3, 4 and 5 and 6. Keeping that in picture, the number of hosts will be 2 to the power 6. So here 2 to the power 6, that is 64, and then we will do a minus 2 as 2 IP addresses are reserved for network and broadcast IPs. So the number of hosts we can have is 64. So we had first we had 2 to the power 6, so it was 64. Then it was then we minus 2 from it, so 64 minus 2 gives us 62. So the number of hosts we can have is 62. At last we will find out the broadcast IP of our address range. As we now know that the maximum number of hosts can be 62. So by default the last IP address becomes the broadcast IP. With that logic, our broadcast IP will be 205.150.65.63. So that's how you manually calculate the subnet mask and associated entities with it. There is also an automated way of doing this, like I found this amazing website. So here you just have to put the IP address and the network range and it will calculate everything for you. So let's put our target IP address that we used in this particular demonstration. And the network range will be 26 and we will hit calculate. So it has given me the address, the net mask, the subnet mask, and the network, the class C. Then we have the broadcast IP, minimum host it can have, maximum host can have, and the total number of hosts it can have. So all of this, either you can do it manually. I will prefer the manual way while we are learning, but as we move forward, we can use automated tools for that. Okay, so before concluding this module, I request you to go through each and every assignments included with it. These are designed specifically for you to test your knowledge on every topic we have discussed here. If you found any gaps that need to be filled, I would suggest to rewatch the videos again and again at your own pace until you get it like the back of your hand. This is for every module we will encounter as we move further. So stay tuned and I will meet you in the next module where we will play with some awesome Linux command line stuff. Alright, so that marks the end of this mini course. I hope you have liked it. If you have liked it, please hit that like button. And if you have any queries, you can dump it down in the comments. And also subscribe to this channel. And if any one of you is interested in learning ethical hacking and penetration testing from scratch and in detail, then you can check out the description for my course link. On that note, I will take your leave and will meet you in the next one. Till then, keep hacking.